Okay, so Mr. You can start.
Okay.
Name your minute of the actual presentation by 45 minutes and no worse.
Sir, I didn't get you. Your sound is not clear.
Can you hear me now?
Yeah.
Yeah, so please limit the length of your talk to 45 minutes maximum. Okay, after that we have 10 minutes of question and answer.
Okay.
Okay, you can begin now.
Okay. Hello everyone. Myself Mustajab Rahman, and the title of my thesis is Cryptanalysis of Symmetric Schemes using classical and quantum techniques.
Mr. You speak little louder, please.
Yes, sir.
Speak loudly.
Okay, sir. So this is the brief outline of our today's talk. So first of all, I will give a brief introduction. Then I will talk about the backgrounds of our thesis, and then we'll move towards the work that has been done in the thesis, which is comprised of classical attacks as well as quantum attacks. And finally, I'll finish my concluding remarks. So the thesis is regarding the cryptanalysis of symmetric schemes. So by symmetric key, we mean that in the encryption schemes where the same key is used for both encryption and decryption. And cryptanalysis is basically mean that we are trying to target the weakness of the ciphers or this such schemes. By targeting weakness, we mean that there may exist some brute force attack or something. So we are trying to attack the system in much better way than that. And here in this thesis, while doing the cryptanalysis, we have considered both classical algorithms and quantum algorithms. So in the classical algorithms that we have considered, we'll talk about that first of all, and then we will move towards the quantum cryptanalysis. So in the background, the classical algorithms that have been considered are boomerang attack and the yo-yo attack. And then in the quantum attacks, there are Grover's algorithm and Simon's algorithm. So the boomerang attack. So this is basically done in the adaptive chosen plaintext and ciphertext scenario. So as you can see by the name boomerang, it is quite obvious that we are sending something and something is coming to us. The attack is quite similar to that one. So in the differential attack, a cipher is considered and there is a differential for a cipher. But in the boomerang attack, what we do, we divide a cipher into two parts, E1 and E0. And for each part, we consider two different differentials. And by combining these two differentials, we are trying to create a bigger differential. So in this way, this gives us the power to actually penetrate more number of rounds. But there is a cost, and that cost is the probability. So as you can see here, so there is a cipher E, and we have divided the ciphers into two parts, E1 and E0. And there are two plain text, P1 and P2, and their difference between them is alpha. So we encrypt P1 and P2 to get C1 and C2, and then we add delta difference to both C1 and C2 to obtain C3 and C4. And then this C3 and C4 are decrypted once again through E1, E0, E cipher E to obtain P3 and P4. Then we check that whether there is some special property of this P3 and P4 or not. Now in this scenario, the special plane of interest is this one, that is the boundary between E1 and E0. Now as you can see here that the difference between P1 and P2 is alpha, and we have considered that, we have assumed that, suppose that for the E0 there is a differential alpha to beta, and for the E1 tail there is a differential gamma to delta. So here with some probability this will come. So in the boundary here, this beta difference will transit, and in this boundary, as we have given here delta difference, so in this boundary with some probability gamma difference will come. And if it's the scenario in this boundary, then we know that this difference should be beta. And again, with some probability, here the alpha difference will come. So essentially, that is what we are trying to do here. We are trying to give a pair of plain text P1, P2 with alpha difference, and by following this procedure, we are trying to get a plain text with difference, a pair of plain text with difference alpha. Now this pair of plain text, two pairs of plain text P1, P2, P3, and P4, this forms a quartet. And what is the probability of this distinguisher? So if the probability of this differential alpha to beta is P, so you can see here we have to pay for this plane and this plane, and this four planes. We have to pay the probability for four of these planes, and that is why the probability of this distinguisher is P square and Q square. Now the boomerang attack is further considered, and it is further actually divided into three parts. So in the previous, we see that there is no dependency between E1 and E0. So now sandwich attack was introduced, and there dependency between E1 and E0 is considered, and that dependency is actually captured by the EM layer. And by considering dependency, I mean that at the end of the beta trail and the start of the gamma trail, there is a link between them. And for that, again, we have to pay some probability, and that probability is R. Now, this dependency is captured by various scenarios. The two most famous of them are ladder switch and the S-box switch. So the ladder switch and S-box switch can only be can be considered if we consider the EM layer as a S-box layer. It will be much easier to understand them. So when you consider this EM layer as the S-box layer, so this is our EM layer here. So in that case, you can see here that the encryption of X is SX and XOR A is XOR A. So again, we add here a B difference, and then we decrypt using the inverse X-box layer to obtain X dash and X double dash. Now, there are two scenarios. Suppose the value of A is 0. In that case, we know that this X and X XOR A are essentially the same value. So whatever may be this B, irrespective of the value of B, will always get this value. So this is the special scenario of ladder switch. And in the case of S-box switch, suppose the difference between S of X and S of XOR A, the difference between these two is B. So when we are actually adding here a B difference, we are essentially just interchanging these two values. So we always know what is the initial difference here. The difference here should always be the same. So again, get the same differential here, same difference here. So these are the two special cases. So in case of ladder switch, as we don't have to pay any probability, so this occurs deterministically. And whereas for the S-box switch, we have to pay probability for only one layer, one plane actually. Now the yo-yo attack. So this is another attack which was introduced by Ronjum et al. For the SPN block ciphers in ACICAP 2017. It is quite similar to the boomerang attack, and this also occurs in the adaptive chosen plain text cipher scenario. Now, what happens in the yo-yo attack? So initially, we choose a pair of plain text P1, P2 with alpha difference. We encrypt them using some cipher and reduced ciphers or something there. Then we obtain two pairs of ciphertext C1 and C2 with suppose beta difference. Now we apply a special operation, that is M swap. We'll discuss this about it later, to obtain new pairs of ciphertext C1 dash and C2 dash, and then we decrypt them to obtain two new pairs of plain text P1 dash and P2 dash with delta difference. Now there is a special property between this alpha and delta, and this property is actually shown by the ACICAP 2017 paper. So this property is this: nu of alpha should be equals to nu of delta. Now what is this nu? So there are lots of questions here. So what is the rounded to cipher should be, and what is this M swap operation, and what will be the value of new? What is the new actually? So new is basically a zero difference pattern. So this new is actually a zero difference pattern. So by zero difference pattern, we mean that so suppose there is a AES state. So in the AES state, there are 4 super S boxes or 4 words, diagonal words. So if you are considering 2 different plane states, A1 and A2, and we are trying to we'll pattern it according to the difference in their words. So there are 4 words in AES states, and if the difference, if a word is active, by active word I means that if the word, if there is a difference in that word, we denote it by 1. If there is no difference, we denote it by 0. And based on that, we will create a pattern 1010, and that is what we call as zero difference pattern. And what is the round reduced cipher there? That is to generate round SPN, which has been identified by Ranjam et al. In the SEK paper. And there is then new is the zero difference pattern. Now, based on that, the Ranjam et al. Have shown this special property for the 2 generic SPN rounds. And as in the last linear layer can be ignored, the property is essentially for the SLS layer. So they have shown that if you take any alpha difference between P and P2 and essentially follow this procedure, you will see that the zero difference between alpha and the zero difference of delta will be same. Now they applied their result to find the first key independent distinguishers for AES, and they also perform key recovery attacks on 5 round AES. Next is the quantum attacks. So the algorithms that are essential for performing the counterattack have been discussed here. So first of all, what should be the adversarial models that have been considered in the attacks? So the attacks that are essentially the classical attacks that we are actually naming them, that has actually been modeled as Q0. So the model Q0 is essentially the classical attack. Now in the model Q1, the adversary is given access to a quantum computer in addition to the model Q, the power of the model Q0. So in the Q1 model, the adversary has no power to make superposition queries to the oracle, but he can do offline computation using the quantum computer. Whereas in the model Q2, in addition of the power of the model Q1, adversary can make superposition queries to the quantum cryptographic oracle. And then there is model Q3, where the adversary can make superposition queries to the cryptographic oracle using differences in the secret key. So in our attacks, actually model Q1 and model Q2 is very much important. And the attacks that have been shown in this thesis are actually in these 2 models, Q1 and Q2. Next is the Grover's algorithm. So Grover's algorithm, what it does actually, it solves the searching problem. So if there are 2 to the power n elements, so using classical algorithms, we can search the whole search in this space in approximately order of 2 to the n time. Or here actually we have denoted to the n using capital N. So we can search using classical algorithm in order of n time. Whereas Grover's algorithm gives us the power to search them in root n times. So this is actually a squaring speed up. And using this Grover's algorithm, the key recovery of the block ciphers, key recovery attacks on block ciphers can be done in much faster way. So we'll see here that, so when we are talking about key recovery attacks, so here we are talking about doing the exhaustive search. So if the size of the key space is 2 to the k, so when we are doing exhaustive search using the classical algorithm, we need order of 2 to the k time, or we have to make order of 2 to the k queries. But using the Grover's algorithm, this gives us a square speed up. So we can recover the key by just making order of k by 2 queries. And this is the power that has been given by the global algorithm in the quantum scenario. Next is the Simon's algorithm. So Simon's algorithm solves the problem of finding the so it solves the problem of finding the periodicity of a function. So using classical algorithm, so suppose there is a function from 0, 1 to the power n to 0, 1 to the power n. So using classical algorithms, we can find the periodicity of that function by making order of 2 to the n queries. Whereas Simon's algorithm can solve the problem, can find the periodicity of the function by making just order of n queries. So it is actually giving an exponential speed up. So the problem that can be solved in exponential time in the classical queries can now be solved in linear time. And the application of this algorithm was first shown by Kuakoda and Mori in their 2010 paper on Lubin-Yakov 3-round Lubin-Yakov construction. Next is the Grobers and Simons. There is a combination of Grobers and Simons. So this combination was first introduced by Gregor Leander and May in the 2019 paper, and and further it was more formalized by Bonnet et al. In 2020 paper, I think. Okay, so they have named it as asymmetric search of a period. So here, what they are doing, they are actually combining the Grobers and Simons problem. So they are actually formalizing a function, and that function is not periodic all the time. It is periodic for some values. So you can see here there is a function f of ix plus j. Now this function is periodic when the value of I is I0. Only then it is periodic. And at that time the period is S. So in that scenario, they use the Grover's plus Simon's combination. So Grover will first find the value of I0 in the order of 2 to the n by 2 times, or whatever it is size, and then the Simon's algorithm find the value of S. So that is why they have combined it. This is a combination of the two algorithms, Grover's and Simon's. Now moving towards the work. So first of all, we will present here the classical attacks that have been done in the thesis. So there are, first of all, there is a niche-lighted cryptography. There is a niche-lighted cryptography candidate, that is FlexAD, which was out in the first round, and on that we performed iterated truncated differential-based attacks and yo-yo attacks, and then we introduced some new cryptanalysis techniques on for the public permutations and for AES-based design. First of all, iterated truncated differential attacks. So this is a internal key permutation of the FlexAD. So here we have shown only the Flex 128 round function. That is, it has a state size of 128 bit, and the blocks of a layer. You can see here that there is a blocks of a layer. This is the linear layer, and then there are S boxes, and these S boxes are AES S boxes. And then there are two keys are used in each round. So this is one round of internal key permutation of FlexAD, and then there's two keys are used in this round. Now we have made some key observations to perform the attack, and these key observations are: first of all, we have seen that there is a special property for the block shuffle. So if there are, so we have the state is divided. So you can see here B0, B7. These are all bytes, and each byte is divided into two parts. So these are nibbles. So we can see that the upper nibble. So these are upper nibbles and these are lower nibbles. So you can see here that if the upper nibble of B0 and B8 are active, after the blocks of a layer, these two nibbles comes to just one byte. So this essentially means that two active bytes after the blocks of a layer translates to a single active byte. So actually this is lowering the diffusion. So this is a weakness that we have observed here, and later we'll exploit that. Next observation that we have done is that the effect of S boxes. So we see here that one active byte here, this actually activates one more byte. And the special property of this byte is that these bytes are always in symmetric positions. So by symmetric positions, we mean that, so this is my left half and this is my right half. The position of this byte in the left half and the right half should be same. So that is why we denote it by symmetric byte. Next observation we made is regarding the AES box. And we see here that if there is an active byte, and this active byte will essentially activate this byte and this byte, but this activeness or the active part of this byte will remain in the upper nibble or lower nibble with probability 2 to the minus 4. So how this probability is coming? Actually, we are getting here that number of pairs that are actually differ only in the upper nibble or lower nibble is 4096 out of the 2 to the 16. And that is why we have that is how the probability is coming as 2 to the minus 4. And the next observation is the super S box. So we have identified two parallel super S boxes in the flex AED, and we see here that we have shown in this diagram that this for the 2.5 rounds. So we have omitted the blocks of a layer here, and rest of the part we consider it as 2.5 round. So for AES 128, we see that we observe that there is a super S box which spans over 2.5 rounds. And in similar way, there are flex 64 design and flex 256 design, where the super S box spans over 1.5 round and 3.5 round respectively. Now I exploit this observation to attack the flex AED, internal key permutation of the flex AED. First of all, to form an iterated truncated differential, we combine the effect of Bloch-Seifel and byte to nibble transition. So we see here that there are two active nibbles, and this will come to a single active byte. And due to the S box, due to the effect of AES S box and byte to nibble transition, we can actually activate only these two lower nibbles or upper nibbles. So over the one round, we see here that these two active nibbles are only activating these two lower nibbles. At the same probability, we can activate also the upper nibble, and this probability is to the minus 7. So we can actually repeat this process multiple number of times, and this is how we are getting the iterated truncated differentials. So this is our iterated truncated differential. So we are repeating the same process multiple number of times, and for actually increasing the probability, we have kept some number of rounds at the end free to get a better probability. And this is the iterated truncated differential for flex 128, 6 round of flex 128. And in similar way, we have also find the distinguishers for flex 64 and flex 256. Next, using the distinguisher, we can retrieve the right pair, and using the right pair, next we have done the key recovery attacks on flex 128. So again, the strategy of the key recovery attack is that so suppose P1 and P2 is our right pair. So we have considered this our initial difference as this, and then we guess these two bytes for the K alpha, the first key of this round, and we see that whether this for each guess values, whether our differential transits to such differentials or not. If it transits to such differentials, then this guess is right. Okay, and then by combining these guesses, we are actually creating a set. So for each plain text pairs, right pairs, we are actually will get to the 9 key candidates, and then we'll use more number of right pairs. So we can use 2 more right pairs to actually to remove all the wrong guesses and to only get the right key guess, and then we'll repeat the process for all other 7 pair of bytes, and in this way we can actually recover the k alpha, the whole k alpha. So these are the complexities of the key recovery attacks that have been reported in this work, and the practicals ones have been experimentally verified in this case. Next is the forgery attacks that have been done on this flexibility. So for forgery attack, we have considered the sequence generation step. So in the sequence generation step, a nonce is considered, and the nonce is first applied on the nonce. First internal key permutation is applied one times, and then there is a special operation inc32, which will increment the 32 byte word. And then you can see here there is a TI and TI plus 1. So these are the sequence for each round, and the difference between the sequence is that these are coming from the TI, and the difference between these TI is that difference between these TIs are only that they are differing by inc32 operation. So if you are considering subsequent sequence subsequent TIs, what is the difference between them? The difference between them is only the inc32 operation, and inc32 operation acts as the JOR with probability 2 to the minus 1. Now it is exploit that to do the forgery attack. So we considered that such type of TI XOR TI plus 1, and we can guess such TI plus 1 with probability 2 to the minus 4. Now, due to the effect of the block shuffle, in the start of the next, due to the effect of the block shuffle, these 2 bytes will be activated, and then we can apply the effect of our AES box and all the other observations that we have done to actually get this kind of SI XOR SI plus 1 in the end. Now, this SI plus SI XOR SI plus 1 can be cancelled out from the associated data or the plain text, and in this way, actually, we can forge a new data. Now, these are the complexities of the forgery attacks. So the attacks that I have shown, that is for the flex 128, and the complexity of this is 2 to the 60, and there also the complexity of the other attacks are 2 to the 50 and 2 to the 80. Next is the UO attacks on flex 80. So in this case, we will use the super S box construction. So here, first of all, the super S box that is spanning over 2.5 rounds is considered, and the linear layer is the blocks of a layer. Now we'll combine these two and we'll directly apply the result of the random metals. And in this way, we can actually design the distinguisher for 6 round flex 128. And next we'll apply by applying the distinguisher, we'll retrieve the right pair, and then we'll use the right pair and to recover the key. And for the key recovery, the strategy that has been shown for the iterated truncated differential has been followed here, and key recovery has been done. And these are the complexities of the UO attacks. And you can see here that all complexities are practical. Next is the UO attacks on AES-based design. And these are actually, the attacks here are on the public permutations. So first of all, we introduced a nested zero difference pattern. So zero difference pattern is there, and on top of that, we added the nested zero difference pattern. So in the nested zero difference pattern, we are not looking only in the words. So these are the AES words, each diagonal here. So in the nested zero difference pattern, we are not only looking in the words, we are also looking in the inside of the words. So this is our alpha 0, and as you can see here that all the 4 bytes are active here. That is why these values are all 0. And this is our alpha 2, and as you can see here, the all bytes are here inactive. That is why this value is all 1. And based on that, we will finally assign the weight. Now the strategy that has been developed in this work, there are 3 strategies that have been mainly developed. The first of all, that is prepend append strategy. Now in the prepend append strategy, so this is our basic EO that has been done on the SLS layer. So in the prepend append strategy, we are actually prepending here some number of rounds and appending here some number of rounds. And what is this now? So from beta alpha to beta, we are adding prepending here a differential, and in the last part from eta to delta, we are also appending here a differential. Now this is strategy, and we are checking whether there is on the using our nested zero difference pattern, we are checking some property here whether some number of bytes here are active or not. And we applied this on the 9-round listing on the ask permutation. This is the AES based permutation, and we reported here first 9-round distinguisher starting from the round 1. Next is the inside out technique. So here we compose impossible differentials. So this is the inverted EO. Why this is the inverted EO? You can see here. So this is our main EO. So now this is in the main EO. Actually, this I1 and I2 in the upper part. So we have inverted this one. Now we start from here. We move here. Then we do the INSOP operations, and then we come here. Now here we add a linear layer. Now this linear layer can be mixed column or some other mega mixed columns layers. And after that, we add here a S box layer, non-linear layer. Now this non-linear layer can be anything. It can be a simple S box layer, or it can also be a super S box layer. And here then, now here, how we are imposing the impossibility here. So we are taking here some difference, initial difference, and then we'll expect here some zero difference pattern. And from here to here, we are actually imposing the impossibility. And based on that, if so we expect in the beta that that impossibility will never occur if our cipher is the ask or the AES permutation. And we applied this on the AES and ask permutation. So we reported here the 6-round AES distinguisher for actually in the known key model. And we also reported the 9 and 10 round and 12 round distinguisher for the ask permutation. The third strategy that we have developed here is the bidirectional yo-yo. So here you can see here we have composed here 2 different yo-yo games and have combined them. So first of all, again we have taken the inverted yo-yo here, and then we have added a linear layer, and then we have again composed here another yo-yo. Now, how the impossibility is imposed here? So here again we are taking some difference, and we expect here some internal difference here, and from the inter to delta we are actually imposing here due to the linear layer. We are imposing here some impossibility, and from this impossible difference we are getting this difference. So as this difference is impossible, this delta should also be impossible. So if this differential is occurring here, we know that this is not our candidate permutation. And we apply this strategy on AES and ASK permutation, and we reported 8-round AES distinguisher in the non-Q model, and we have also reported 16-round ASK distinguisher. And these are the distinguishers that have been reported in this work. So there are 6 distinguishers for the ASK permutation and 2 distinguishers for the AES in the non-Q model. Next is the boomerang attack. So in the boomerang attack, we have actually combined the yo-yo with the boomerang. So this is our yo-yo and the boomerang. So there are some difference between them. So in the yo-yo, this is a deterministic distinguisher, and this is mainly related to the patterns. So there is a zero difference pattern for alpha and zero difference pattern for delta, and we know that this two zero difference patterns should be equal in case of yo-yo.
You have 10 minutes.
Okay. And in the boomerang attack, this is probabilistic, and this is actually related to the actual differences. This is not related to the patterns or something. Now we combine this in this way. So first of all, we observe that the MSOP operation in the yo-yo for the yo-yo case is actually a combination of the ladder switch and the S-box switch for the boomerang. So we observe that, and in this way, we try to combine these two different strategies. And how we are combining them? So initially, we take again for the upper part, we take an initial difference alpha, and here, when we are doing the yo-yo attack, we are actually doing here what's our mega swap operation. But now we'll not do the swap here. Now we'll add some different difference here, and we'll add the difference in such a way that here the M swap operation or what swap operations occurs automatically. And in this way, the M swap will be done here, and we'll expect that the zero difference pattern for alpha dash should be equals to alpha. And in this way, we have been able to actually, so if you're considering the boomerang framework, we have been able to we have been able to increase the probability to Q square Q. But here is the thing that for now we have been able, our condition is that UN layers should be simple enough. So if you are able to make this a complicated one, then if you are able to include more complicated layers in the U1, then we will be able to penetrate more number of rounds. Now we have applied this strategy to mount key recovery attack on 5-round AES and 6-round AES, and also to mount 10-round key recovery attack on 10-round Falcos. And these are the complexities that have been reported in this work. Next is the quantum attacks. So there are two topics in this. First of all, there is quantum attacks beyond Grover search, and then there is quantum resource estimation of the Grover search. So in the quantum attacks beyond Grover search, we have applied the Simon's algorithm in the Q2 model and the asymmetric search strategy in the Q1 model. So we have mount attacks here on hash counter, tweakable hash counter, and SCH constructions. So for the hash counter, we have used the asymmetric search strategy to mount Q1 attacks, and we have also used the Simon's algorithm here to mount the Q2 attack. And for the tweakable SCH here, we have used the Simon strategy to mount Q2 attacks. And for the SCH construction, we have used the asymmetric search strategy to mount Q1 attack, and for the Simon algorithm to mount the Q2 attack. Next is the quantum resource estimation. So here what we have done, we have actually, we know that there is a generic attack using the Grover's algorithm on the block cipher. So, but The essential question here comes is that how big a quantum computer should be to mount such attacks. So we have tried to answer that question using this work. So for that, we have considered two lightweight block ciphers, current and present, and we have designed quantum circuits and Grover oracles for both of these designs, and we have implemented these designs using the Project Q framework, and there is a special operation in the Project Q that is it can it can estimate the resources that are required in an automated way. So we have used that tool and we have estimated the resources. And these are the results that have been reported in this work. So you can see here there is a max check operation to the 40 to the 64 to the 96. This essentially actually this is from the NIST PQC post quantum cryptography criteria. So this essentially tells us what should be the maximum depth of the circuit. So we have considered different depths according to their criteria, and based on that we have reported how much resources are required in such cases. And this is the result for the present. And finally the concluding mark. So here in this thesis we have actually done classical and quantum cryptanalysis, and we have combined two different strategies that have been reported 20 years apart. So first of all, there is a boomerang strategy, and then there is a yo-yo strategy, and we have extended the yo-yo strategy, and we have combined these two strategies to report new cryptanalysis techniques. And also we have done the quantum cryptanalysis. We have reported the size how a big quantum computer should be to mount Grover's attack on some lightweight block cipher. And based on that, we can tell that our next question should be that essentially till now we have seen that there is a lot of work on the Simons and Grover's algorithm on the symmetric ciphers. So what should be the impact of other algorithms, quantum algorithms? There are a lot of other quantum algorithms. What should be the impact of those algorithms on the symmetric ciphers? That is still unknown. And for the resource estimation framework, till now people are doing, people are considering different ciphers, and they're considering different ciphers and doing the resource estimation in a different way. So development of a common framework for the resource estimation such that it generalize all the block ciphers, or at least a class of block ciphers, and then it estimate the resource automatically. So development of such a resource, whether such development is possible or not, this is also an open question in this case. And this is my list of publications. And finally, I would like to acknowledge my supervisor, and then there is Dr. Jivan Saha from Deciphered Lab, ITF, and other members of our lab. Thank you.
Okay, so any question, Professor Adversarial?
Yeah, thank you for your nice deliberation, starting from classical to quantum. So you brought forward few of the ideas like extension of yo to boomerang and all, combining those two, and then using that in your classical, from classical to quantum algorithms for attacking few symmetric equator systems. So my point is, I have just gone through all the reports of the reviewers as well as your supervisor. Few comments were made, and you have already modified them in your latest version of your thesis. So few questions, like what are the extra advantages that you got when you combine the yo-yo and yo model and boomerang? What extra benefits that you obtained compared to others previously proposed schemes. Can you please explain a bit?
Okay. So I'm moving to that slide. So when you are actually this framework, this is quite like the boomerang attack. Okay. But for the boomerang attack, we need to pay the probability P square Q square. But we are still here following the same framework, but here the probability is increased. So here instead of P square Q square, the probability is P square Q. But the main problem, as I have already mentioned here, that in our case, till now, we have been able to identify simple U1 layers. So, like the boomerang attack, if we are able to actually add more complicated U1 layers, then we can actually penetrate more number of rounds. So till now we have not been able to penetrate more number of rounds, but if we are considering only the framework here, we've been able to actually improve the probability.
Okay. Another thing that you mentioned about like E0, E1, and in between you might have some EM to get more facilities. Have you ever thought anything about not only E0, E1, but in between EM as well?
Okay. So, sir, actually here the thing is that actually our E1 layer here, actually this is not only E1, this is actually a combination of EM and E1.
Okay.
So that is another actually that I have also reported in this work, that if we are able to actually distinguish these two parts, EM and E1, then also we can actually penetrate more number of rounds.
Okay. And in case of quantum attacks, like what exactly new things that you developed? You just estimated the resources. That's no doubt it's a good idea. So what exactly the new algorithm that you proposed? Could you please just, you were very fast on that part, so I couldn't get it. Yeah.
Okay. So actually, this asymmetric search, this was actually introduced by Bonnetten et al. But here in this case, they have actually, and this was only done for even Mansour cipher. But here we extended this part and we redesigned the algorithm for the SCTR. So we are not here actually develop something from scratch, but we have taken the algorithm and here we have modified this part for SCTR and its variants.
So actually, I would like to add something here that so the model, we did not create a new model here, so we did an existing model. However, the model is not regularly just applicable to arbitrary construction. Okay, so earlier works demonstrated the model on few constructions, and we showed that by some tweaks and tricks, the same model can be fitted to have some new constructs like the CTR and its variants. Those were not done before.
And how practical is Q2 and Q3 models are? That means they're using this quantum machines. Like, could you please go back to that slide where there's Q1, Q2, Q0?
Okay. This one, sir?
Yeah, this one.
Okay.
Yes. So this quantum cryptographic oracles means, what do you mean by that?
So quantum cryptographic oracle, by quantum cryptography, I mean that an oracle that accepts superposition queries.
Okay. And
so there is a yeah, sir?
Yeah, please continue. Yeah.
So there is a classical oracle. So this is our normal oracle. In addition to that, here this oracle actually accepts superposition queries. So in this model, actually adversary can make quantum queries to the oracle.
Okay, that means you have both access to quantum computers as well as the classical oracles as well as the quantum oracles, right?
No, here classical oracle is considered. Actually, yeah, we have access to a classical oracle also. In addition to that, I have also access to a superposition oracle.
Okay, and this access to the quantum computers for practical models, how do you think that, how much, I'm not very aware of the local state of art, I mean the current state of art. So what is the current status? Like access to a quantum computers means what actually?
Access to a quantum computer means that, so till now there is IBM machines that are actually publicly available, I think 18 qubit. So we cannot do more realistic attack on that. But if there are bigger machines coming in the future, then maybe there is a possibility. But for the superposition oracle, there is a little bit of controversy in this case, because there are people that are quite opposed to that one, that they have considered is quite superficial also. But because there is a less probability that actually if there is a less probability that people will actually give access to make superposition queries to their system. Till now, this is there is a less probability for that, but this is quite possible. The model Q1.
Okay, and in case of till now, IBM does have 18 qubits, and for your case or for the normal attacks, how much qubits are required?
IBM has actually the 18 qubits is publicly available, but there may be some more systems with much more qubits also. But in this case, the number of qubits that we require actually this much more. So this our attacks that we have reported here are not practical in the current scenario.
Okay, so how much it requires for qubits?
So for SCTR, actually we need 2n qubits. So that is so if there is 128 bit.
We can show the table, sir.
You made a table, I think. The data complexity and all.
Oh no, sir. That is for actually. That is for actually mounting the Grover's attack.
So that table is not there. Okay, so you can mention then verbally that, let's say if pure classical attack, what is the best known pure classical attack, what is the complexity, and if you add this quantum oracle that you want to model, then how much that complexity is. So it may be practical or it may not be practical. But the idea is that had the classical complexity been lower, then the quantum complexity would be further lower. So that is the base. That you can just mention your numbers. The base classical attack versus the complexity of the attack using these two models. So you can mention that.
Okay, so first of all, sir. There is actually how can we actually compare the classical one with the quantum ones? So because when you are using the effect of Simon's algorithm, this is giving us a linear complexity. So this is in the order of 2n or something. So it is one.
That's right. So for example, let's say 128 cipher, you can compare the complexity, right? One would be to the power, let's say, based on attacking classical to the power 120, and one can to the 197. Just for example, I'm saying.
Okay, sir.
So from that angle, okay.
Okay, so complexity wise, for SCTR, the attack on SCTR requires order of 2 to the n queries actually, order 2 n queries, linear, in the linear form. So it needs approximately order 256 queries. But the main problem here, what should be another question? But here comes another question that how our quantum computers be so that we can actually attack such systems only with 256 queries. So whereas on the HCTR and these things, the classical attacks are in the exponential terms. But using the quantum attacks, in the quantum algorithms, we can perform these attacks in linear complexities.
So here the queries means quantum queries, right?
Quantum queries.
Okay. Okay, fine. So yes, so thank you very much for answering all these questions nicely, and you made a very good presentation, very compact presentation. So thank you very much.
Thank you.
Okay, I don't have any further question. Anybody else?
Thank you, Professor Vitali. So any other audience? You can also ask or comment any question.
Hello, Mustafa. This is Himan. Yes, it's a very nice presentation. Just one query that you mentioned that in this project Q, you have some automatic way of doing resource estimation, right?
Yeah.
So, and then you mentioned that you need a common framework for resource estimation. So, is this automatic? Means in the open problem, you mentioned that there should be a common framework to find out about this. So, what is this? What does that question mean with respect to this already existing framework in Project Q? Is it limited in some way, the Project Q framework?
Oh yeah, actually, in the Project Q framework, we are actually first designing our. So for a present block cipher, suppose we are designing the present Grover oracle for the present block cipher, and then we are applying the automated that module, automated resource estimation module. But by common framework, I mean that we don't need to design separate oracles for present or block cipher. We'll specify some parameters, and based on that, if we can actually, in an automated way, oracle is being designed, and then the resource being estimated. That's what I'm trying to mean.
Okay, fine. So there is some pre-processing needed as of now, and the common framework will help us get rid of that pre-processing.
Yeah.
Okay. Thank you. Yes.
Any other question from any other audience? If not, then let's thank the speakers.
So let me semi-congratulate the speaker, because you are not yet proper doctor, but soon you will be. But that's why a semi-congratulation to you. So thank you.
Yeah, thank you all for attending. Thank you, Professor Vitali. Thank you all the students and all the faculty members that they are present. Okay, so I am now formally closing this meeting.